Hello friends, welcome to my channel. Let's have a look at problem 259, 3 sum smaller. So this problem actually concerns the counting of the number of valid triplets. So here we are going to give a treatment using two-pointer trick. First, let's read through the statement to digest the problem requirement, and then we do a simple analysis, and finally we share two formats of code. First, let's look at the statement. Given an array of n integers called nums and an integer target, find the number of indices triplets I, j, k, with I, j, and k are increasing and in bound that satisfy the condition nums I plus nums j plus nums k is strictly less than target. So here are three examples. So example 2 and 3 are sort of edge cases. In example 1, so the output is 2, and in the explanation, the problem statement lists the two indices, the corresponding numbers actually. So with that said, let's look at the constraints. First, the length of this nums list is bounded below by 0. It means it can be empty, and bounded above by 3,500. So the range of the elements in the list and the target itself is in between -100 and +100, with both ends can be included. So with that said, let's look at the method. So here our method is the standard two-pointer trick. So this problem actually can be regarded as a variant of the classic three-sum problem. So in this problem, two observations are important for us to address the problem. First, we could sort the nums list. The reason is that as long as we have three distinct indices I, j, k, such that nums I plus nums j plus nums k is less than target, then they will yield one valid triplet that satisfy the problem requirement. So we just need to use the smallest one as the start, the middle one as the middle, and the largest one as the end, right? So this is the first observation. And the second observation is that, so for this problem, for the method we're going to use, in other words, the two-point trick, the sorting or sort is important. After sort, we gain something. So we could fix one number, and then we try to find how many valid triplets that starting with that fixed number and satisfy the problem requirement. So here is the counting principle. So let's first fix the left pointer, right? Given a fixed number, so we fix the left pointer L and the right pointer R. So if the fixed number, which corresponds to an index, say I, then plus nums R L plus nums R is less than target. In other words, the equation star. Then actually we can get L minus L valid triplets. The reason is that they have a 1-1 correspondence with the below triplets. So here is fixed nums L and nums J. So for all J is in between L plus 1 and R, both ends inclusive. If you count the j's in this range, the number is R minus L. So notice that in this triplet, so the indices are not maybe not in the smallest to largest order, but it corresponding to 1 with the correct order. So that's the second observation. So actually, for a fixed sum and a given L, assume R is the largest right pointer such that star holds. Then we have that if L1 is less than L2, then R1 is no less than R2. So this monotonicity is actually what makes the two-pointer sliding window idea effective. The reason is that we do not need to check R from n-1 towards left when we examine larger pointers. So before we write the code, there are some extensions. For example, can you do three sum larger? So you can actually, for this, you can do iteration from in the reverse fashion, or you can sort with decreasing order. So with that said, let's look at the coding. So first, I'll write one format, and then we will do a slight change to yield another format. So this is the two-pointer trick, right? So for this, first I'm going to sort this nums, this list, just so that we do not forget it. And then let's get the length of this nums array. So this is m. And then we can iterate over the nums and then try to find the contents of the valid triplets. So for this, I'm going to iterate for I in range. So here we need to n-2. The reason is that we need at least three numbers, right? So the last index k should be less than or equal to n-1. So for this, we are going to find all the triplets starting from this number. Let's call it fixed. So this nums I. And then for the remaining part, we're going to run the so-called two-pointer trick. So it's like two-sum problem, right? Two-sum leg. So let's write it like this. What we are going to do is that let's initialize L to be I plus 1 and R to be n-1. And then this is the standard while loop. So while L is less than R, what we are going to do is to check if fixed plus nums L plus nums R. So if it's greater than or equal to target. So in this case, this is still too large. So we're going to decrement R by 1, right? So here I'm using if condition, right? Else, what we're going to do? So if the fixed, this sum is less than target. In other words, so using the fixed and using the left number, and then the right number actually is the sum of the three is smaller. Then we can compute we can use the last one for all the index in between L and R. We do not include L for sure. So in this case, the counting result is R minus L incremented by this one. Once we finish this for all the valid triplets, starting with this fixed and starting the middle at L, then we get all this. And then we are going to increment L by 1. So this way, so we basically take the root that we fix this number and find all the middle elements corresponding to L and corresponding to the right? And then what we're going to do is to return the result. So this is one format of solution. So here I'm using if-else condition. So let's do a check quickly. So our result, let's initialize this to be 0. Then we get one example passed. Now let's look at generic case. Yeah, it passes all the generic case. So next, I'm going to change a little bit for the code to follow another slightly different but thought, but along the same line. So here I'm going to use this one as V1. So actually we can sort of copy this part also. So we copy this. So all this are the same result in, and then so when we do this, so actually we want to change a little bit. So then what we are going to do is for each L, we find the largest right pointer such that the star in our annotation part holds. That is this one, right? Then all the smaller r will also satisfy the condition, right? So what we are going to do is we use another while loop. While r is greater than L and fixed plus nums L plus nums R is greater than or equal to target. So we are going to decrement R by 1. So this way, once we exit this while loop, so we have two conditions. Either is R less than or equal to L, or this sum is strictly less than the target. So then we are going to increment our result by r minus l, right? So this way we find all the triplets starting with fixed and the middle with nums l, and the right we vary the last. We find all the possibilities for the last number. So notice that here the increment can be 0 if r equals l, but it's still okay, right? So this way we find for each of the l, we find the middle element, we find the corresponding last elements. Then we can actually increment l by 1. So this is the second solution format. Personally, I feel that the second solution format is more, it's much easier to digest or much natural in some sense. But essentially, the two formats are the same. So with that said, let's do a check. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes the generic case. So with that said, actually that's about it for this video. In this video, we explained the two-pointer method for this problem. And here we want to emphasize two things. So one is the sorting, which is important for this program to be valid. And the second, so we tweaked the code a little bit to tailor slightly different thoughts. So with that said, that's it. Thank you.